Hi everyone, welcome back to Everything Mathematics. In today's lesson, we are going to be proving trigonometric identities. I have selected two identities that we are going to prove step by step. Before we begin, we are going to make some assumptions. We will assume that you are familiar with this Pythagorean identity and that you are familiar with this reciprocal identity. I have a few tips here that you may want to put into practice whenever proving identities. Let's take a look at the first one. The first one is saying that whenever we start the process, we always have to begin by picking a side. And then we want to work the side. We want to do algebra to it to obtain the other side. Well, which side do you choose? The side that you want to choose is the one that looks more complicated, the one that will allow you to do more algebra so that hopefully you end up getting the other side. So pick the one that seems more complicated. Number 2 says that if you have expressions involving secant, cosecant, cotangent, think about re-expressing those expressions in terms of sine, cosine, and tangent. Number 3 says that if you have fractions, think about common denominators. Number 4 says that if you can apply any of the identities that you already know, like Pythagorean identities, reciprocal identities, you may want to use those identities to be able to do clever substitutions in order to simplify. And again, I'm going to show you what I have in mind. And number 5 says, if you have a fraction, think about multiplying the numerator and denominator by conjugates. That's very useful tip. And again, I have an example here that you're going to see that in action. And number 6 says factor. If you have quadratics, if you have common factors, think about factoring throughout. In this particular example, they're asking us to prove this identity, and I think that it is a no-brainer that the left side is the more involved side, so we're going to end up picking that side. Also, I noticed that there we have two fractions, so we should start thinking about a common denominator. So let's get started. I'm going to start by rewriting the left side, 1 over 1 minus cosine theta plus 1 over 1 plus cosine theta. Then we're going to go ahead and get a common denominator. So here I will multiply top and bottom by 1 plus cosine theta. And the same thing over here, 1 plus cosine theta. Here I will multiply by 1 minus cosine theta and 1 minus cosine theta. Now in the next step, I'm going to put everything over my common denominator, which is 1 minus cosine theta times 1 plus cosine theta. That's what I have. In the numerator, I'm going to be multiplying this expression by 1 and the same thing over here. So we're going to end up getting 1 plus cosine theta and 1 minus cosine theta. Now you notice that we can simplify the numerator because I have cosine and minus cosine. So I'm going to go ahead and cancel these two terms. So now the numerator will simply have 2 divided by the common denominator, which is looking a lot better. Very nice. However, the expression that I have here does not match with this expression right here. So then that means that we need to do a little bit of more work. We need to invest more time on this expression. Notice how the denominator right here is in factor form. So maybe what I should do here is to expand it, to FOIL out. And if I do that, we're going to end up getting 1 minus cosine theta, then over here plus cosine theta minus cosine squared theta. That's what I have right here. Then you notice again that I can cancel these two terms right here. So that will disappear. And then I'm going to have 2 all this divided by 1 minus cosine squared theta. And I want you to look at the expression in the denominator. That expression can be replaced with something simpler. Let me remind you of that. So I'm going to take you right here to the top of the page. So remember the Pythagorean identity that sine squared theta plus cosine squared theta is equal to 1. Now I'm going to take this expression and I'm going to solve for sine squared. That means that we're going to have that sine squared theta is equal to 1 minus cosine squared theta. And this is the expression that I will now use. For example, here I have 1 minus cosine squared. And here I have that 1 minus cosine squared equals sine squared theta. So all of this over here can be replaced with sine squared theta. Let's go ahead and do that here. So we're going to have 2 divided by sine squared theta. So much nicer. Now, it may be obvious to you that this now simplifies to this expression on the right, but in case it is not, I'm going to go ahead and regroup my factors. I'm going to put that 2 first over 1, and then times 1 over sine squared theta. And I want you to notice that I didn't change the expression. 2 times 1 is 2. 1 times sine squared is sine squared. But now it is obvious that this expression right here is cosecant squared. So we're going to have 2 times cosecant squared theta. And now we are completely done. This expression matches beautifully with the original one. So then that means that we proved the identity. We are done. We are completely done. Here now we have another identity. And if you look at this identity, both sides are pretty comparable in terms of difficulty. I don't think that I can say that one is easier than the other one. So I'm just going to pick one and see what happens. I'm going to pick this one and I'm going to try to work it out. So starting, we're going to have here sine x divided by 1 plus cosine x. When you look at this expression, I don't see any squares or anything like that. So I cannot start applying my previous identities. So the only thing that I noticed here is that perhaps we can multiply by the conjugate of that denominator. Now, a quick refresher in case you forgot about conjugates. If I have a binomial a plus b, its conjugate is a minus b. And vice versa. The conjugate of a minus b is a plus b. Now, the benefit about multiplying conjugates is that when we multiply them, see what we get. We get, if I FOIL, I'm going to have a squared minus ab plus ab minus b squared. And then notice how those terms cancel out and you nicely get a difference of squares. So in this case, if I multiply top and bottom by the conjugate of 1 plus cosine x, I'm going to have 1 minus cosine x over 1 minus cosine x. And then in the numerator, I'm going to have sine x times 1 minus cosine x. I'm going to leave it like this for now. In the denominator, I'm going to have 1 plus cosine x times 1 minus cosine x. So those are the two conjugates. And I already know what I'm going to get in the denominator. Remember here, if you multiply conjugates, you get a difference of squares. So I'm going to have here 1 minus cosine squared x, a difference of squares, because remember, 1 squared is the same thing as 1. And then in the numerator, same thing as before, sine x times 1 minus cosine x. Now from the previous example that we just did, remember that 1 minus cosine squared is equal to sine squared x. So I'm going to take advantage of that. I mean, by having sine squared x in the denominator, things are considerably simpler. So I'm going to have sine x times 1 minus cosine of x, all this divided by sine squared x. And now, having sine squared is like having sine x times sine x. So I can now cancel this sign with a sign in the denominator. And that is going to give me 1 minus cosine x in the numerator all over sine x. And if you notice now, this expression matches beautifully with this one right here, and that says that we proved the identity. All right, everybody. I hope that you really found this helpful. I hope that you enjoyed this journey of proving identities. It is a lot of fun. Again, sometimes it is going to be frustrating, especially if you're having difficulties proving the identity. But with practice, you're going to get better at it and you will be able to find more success. Bye for now. Until next time.